go. Let's
Yeah,
start.
so
Mm.
so this presentation is based on professor's work on simplified algorithm for order-based maintenance. So uh, in this paper is a simplification. Uh, so this presentation uh, here in my job is to like narrow it down. I check whether the description in the paper given is actually true or not. Like it's not any new algorithm or any new proof. I'm just like elaborating what this paper actually didn't include in the final version.
Good. Go on.
Okay.
Mm.
Uh, so the whole presentation, uh, let's give it- so the whole presentation is based on this single line: insertion into the order data structure, including any relabeling, cost O of one, amortized.
What is the amortized?
We'll get to like every terminology with the like related flows and papers. So just hang in there.
Mm.
So so mainly the paper states it, it doesn't explain it, and the half page it gives describe a structure that probably cannot reach that bound. So you we will also check why. So basically, mm, uh, if we only consider the uh, order data structure, it shouldn't be possible. But the O of one claim is still correct. We will also see why. And in the final algorithm and in the final time complexity, we can see still a logarithm value, which also doesn't come from the order data structure. We will also see where it comes. Like basically, it's from the uh, mean priority queue. So these are the three things we will uh, look at look into today.
Okay. Now come back. So, why you say the single level is login? Here explain now briefly.
Yeah, these things are actually explained later down the slides.
Mm.
So basically, a single level labeling cannot achieve the O of one claim which the paper has. So for that, the paper actually does like a simple modification to
Mm.
the labeling system that enables the O of one was amortized RAM complexity.
Okay. So your presentation focus on this part, right?
Yeah,
Why
the O
why
of
it is login? Single level is login. Yeah.
uh, the explanation is there and we will
Okay.
see. So
What
basically,
okay,
yeah,
good. Once you say the once fixed, the remaining is not. I cannot understand this. Is some errors?
no, it means like in the final time complexity, we can still see a logarithmic time complexity, but that doesn't come from the order data structure. That is solely from the like mean priority queue.
Mean priority queue. Oh,
There is
really?
also a priority
I
queue, right?
okay. Okay. Yes, I
So
expect to explain this in detail. Yeah.
yeah, it's there.
Mm,
So like there is a logarithmic time complexity. So
mm,
people might expect that that might be coming from the ordered data structure, but no,
mm,
that's for the mean priority queue.
mm. Okay.
So this is basically the roadmap of the presentation. So we
Mm,
discuss the like preliminaries, what
mm,
is K core, core orders, core
mm,
numbers, and everything. Then we like dig into the main part of the presentation. So as we all know and heard like hundreds of times, what is like K core and core number? Basically, K core is the largest subgraph of G in which every vertex has degree at least K. And core number, also known as sometimes coreness, is like for a vertex V, the largest K such that V belongs to the K core. So it's just the number of a vertex, which is the largest K number. So in general, in like static graphs, the computation is easy, O of M, repeated peeling of minimum degree vertices. So it's basically the BZ algorithm. But we are not here to talk about this because we will somewhat focus on the core maintenance to understand what's happening. So uh, so the core maintenance is this: one edge changes and it updates every core number without recomputing from scratch. So this is our goal. Uh, but this process is made a bit easy by these two theorems. First, one edge updates move any core number by at most one, and second is all the vertices that changes share the same core number k, and they sit in a connected region around the inserted edge. So these are the two theorem for the core maintenance, which is needed to run core maintenance algorithm properly. Like I'm
Oh,
not.
sorry, Pierre. You said two facts make it tractable. What means of tractable?
I mean, easier to do, like possible.
Uh, it's possible.
Yeah, it is
Okay.
just a choice of word.
So you say this one and this one. I don't talk about order. Yeah, it's possible. It's possible. Maybe
Yeah,
not
we
fast.
we
It's possible. Yes,
we
correct. Yes.
yeah, we don't have to dig too deep into the core maintenance. Just we need to know this theorem because like these will come in handy in some point. Uh, so there is also an asymmetry lives in the uh, core maintenance. So the asymmetry is basically removal is very easy. Every vertex you examine is a vertex that changes. So the uh, search set is basically V star. V star means we have the set of vertices which core number actually changes.
Hmm. O- Okay. You said insertion and removal are asymmetry. Why?
Uh, Sorry.
Why? Why they are asymmetry?
So basically, that's another whole big topic of
Yeah, okay. Just explain
yeah.
the keywords in your
So
key.
the edge removal is basically bounded.
Mm,
So bounded means we know the like domain where we need to search.
mm.
But for edge insertion, it's basically unbounded.
Why is unbounded?
Uh, like
Okay, same words. So what is the worst case? If you say it's unbounded, what is the worst case?
what is the worst case that every vertices of the graph changes?
Yes. Uh,
Yeah, but yeah, that's so that is the main issue in core maintenance, that it's asymmetric and the insertion is very expensive. Then
You
we
said
go
the
to the
insertion is expensive. You're talking about the worst case, best case, or average case. Which case?
in average cases. Mostly
Are you
like compared to the edge removal, insertion is expensive.
so what? Sorry, in average case, in which case? Pardon? In which case?
Sorry.
In which case? You said the insertion is less expensive than removal.
In average case.
How do you define your average case?
So it's basically depending on the region of the graph, right?
Mm,
So in a like densely populated area where maybe the k number is high, so an
mm,
insertion will cost a bit more because several other vertices are also connected with the insertion, and those core numbers will update as well.
Partly correct. Yeah. Uh, go on.
Okay, so then we have the k order. This particular topic is also a bit confusing to me as well,
Mm,
but I'll try to explain it
yeah.
as
Okay.
best as I can. So as we can see, insertion is expensive in the previous slide. So basically, since it's expensive and like my goal is to insert just one vertex and it has to update like maybe hundreds of more other vertices. So insertion does some wasted work. So there's no way to like avoid it. So our goal
Oh,
is
okay. Why do you say it's wasted work? What is the wasted work?
our goal, like actual goal is to
Mm,
insert a vertex, right?
mm.
So we want to
You
insert a
said the
vertex.
age, not a
Oh,
word.
sorry.
Age. Yeah.
Insert an edge.
Go on. Yeah. Yeah.
But
Mm.
to insert that, we also need to update like surrounding core numbers as well. That is like a byproduct of the work because we didn't want to update it, but we need to update it. That's why we like it's sort of a wasted work which can like cost computational power.
I
So
I don't think you defined clearly here. Wasted means the searching range is much larger than the update. The searching vertex is much larger size than the uh, updated vertices.
yeah,
This is
like
the wasted. Wasted.
yeah, my argument is like it's sort of a byproduct that we
Mm,
have to do for an insertion.
mm. Okay,
So
go on.
uh
Mm.
so our goal is to be how can we uh waste less. So there for this the k order comes in. So basically the k order is we are keeping the order when we are peeling the whole graph. So as you know, the BZ algorithm actually peels the whole graph uh, in like an onion. So first the smallest core number goes first, then we go to the like denser and denser region. But for the k order, we also record that order which is being peeled first and which is later. So what is the gain here? So without that order, an insertion does not know where to look. It searches like every direction. So the V plus becomes very large. And That becomes, since the V plus becomes very large, the searching domain also increases, and that becomes costly. So if we have the k order, this lets the algorithm to stop early in the most vertices that cannot change the V plus.
Yeah, you say the V plus shrink sharply. In which case? And
Sorry?
why? You said using the keyword the V plus shrink sharply.
Yeah.
So in which case? Best case, worst case, or average case?
Uh, I don't understand like the question.
So you shrink sharply. You are talking about the V plus shrink sharply. I just asked you in which case it shrink sharply. In the worst case, it shrink sharply.
No, like it shrinks sharply means like when we have the order,
Hmm.
the peeling order, then we don't need to like search the whole graph.
So my question is, in which case it can shrink sharply? Are you sure? Are you sure is in the worst case it can still shrink sharply?
No, I think it's in the best case.
Is the best case? Yeah,
Yeah, I think
best case. So can you give us an example of it cannot shrink sharply in the worst case? Worst case example.
worst case example.
Mm.
I am not particularly sure if it's correct, but uh, maybe I think if the graph is such that uh, the layers are very low, like there are very so there are the we have few layers.
Mm.
Suppose we have uh, suppose there are like only two or three layers of the graph, and
Mm.
most of it's maybe just lower layer, like a core number of one, then
Mm.
I think it won't shrink sharply.
Mm. No, maybe it's not a worst case.
Then I'm not
Yeah.
quite sure.
Okay. Uh, uh, the worst case, you must carefully construct this worst case, like a chain graph. The graph is a chain, like a list. This will trigger the worst case. This is the one simple example. But mostly, there's a no graph like this, chain. If the graph is a chain, it's called the list, not the graph.
Okay. So so basically we found that uh, we need the k order so that we can reduce the searching domains. But this order is not free. Every insertion or removal can move vertices between core levels. So the order must be updated too. Also, uh, also the WAG keeps like asking one question: Does vertex U count before vertex V? So as we can see here, the K order actually helps, but it's also expensive. So let's see like how we can reduce the cost for the K order. Uh, so here is a summary and a comparison between two papers, one from professor's paper and one like a similar paper from 2017. So that paper actually had the uh, time complexity of log O of k, but the professor has O of 1. And like, yeah, this is just a comparison. And we can see the improvement here if for the insertion bound that part for the from the previous one and the new one. It's just a simple comparison.
We okay, come back. So Here we understand it. Here we use order data structure. How about here? Why?
So it's because of the minimum priority queue.
Mm. Yes. No, no, no. You can explain clearly. So it's priority queue for what?
Uh,
Why? The why here is E plus. Why here is OK. It's both are priority queue. So main heap is also priority queue, right?
yeah,
It's implemented by heap.
yeah,
Here is the priority queue.
yeah.
It's also implemented using heap. Why is the difference? Is one is OK and one is E plus? Does this means OK, the size of OK is equivalent to E plus?
No, E plus should be smaller.
Why? Yeah, that's a key question. Why?
Uh, I think it's because like how uh mm, how the minimum priority queue handles the vertices. It only updates the uh, touched vertices here as
Uh,
we have
which one update touch the vertices? This
for
one?
the minimum priority queue.
This one?
Yeah.
Okay. But the why here is OK.
Um, I haven't gone to that particular paper in
Mm.
details. So it's just a comparison. I pull it from there.
Good thing. Your answer is correct. Yeah. This one is so this one is only updates the connected connected edges. Connected what is the connected ones. So this one is E plus. E plus is the connected ones. But the OK is for the whole
Whole,
list of the vertices in the whole list of all the vertices with the core number K. They maintain all of that. That's
yeah.
for their implemented. They use a binary substrate to implement this. Mm. Good. Go on.
Okay.
Mm.
So here we have like also it's just a comparison with some papers and how like we our focus is just these two.
Mm.
So uh for the first row we can see
Okay. Here, I just ask you simple question. Why they use big O? It's all the others use big O. What do you mean? What does it mean big O? Why they don't use this one and this one?
yeah because it's the upper bound
Mm.
and also like it's I'm not sure for the second one but the
Mm.
uh
Yeah. What's this
the
one?
first one is because it's like amortized.
So I say, do you mean this one?
No, the first row, this
This
one.
one?
Yeah,
Okay. This one. Mm.
yeah,
All the comparisons. Okay. All the comparisons are all using all the data structures.
yeah.
Okay. This one is we talked. Well, why is this one has the log? Okay.
It's the previous one we see.
Yeah. Can you explain the why? Why is log okay?
Uh,
Why
it,
is
it,
this user tree is log okay?
yeah.
It's covered in lectures, you see? Tree.
So if we don't use the like if we use like a single labeling
这往
system.
哪里？Wait，我在上班，你就往哪里去？往哪里去？ So I say the why it is this one as log okay in a tree.
So if we don't use the if we use a single leveling system, then the order cost is always logarithmic value, right?
Sorry, which data structure using?
In order based.
My question is here. Why you see is we are a tree? Why use the tree as a log? Okay, you don't
It's
know?
it's because the tree's uh, time complexity,
Yeah.
height.
Hmm. Yes. Is are you sure if tree is a binary search tree or balanced tree?
Sorry,
So this tree is which kind of tree? Is it binary search tree or balanced binary search tree?
one there was one was balanced. I'm not sure if it's this one or this one. One was balanced.
So which one? Are you talking about which one?
I think this one was a balanced tree
Yeah, why the balanced tree is log okay?
because of the height of the tree.
Yeah, continue. Why the height of tree is yeah height of tree? Tell me the height of tree balanced the height of tree in a balanced tree is what?
Uh, H equals to
For example, red black tree. So what's the height?
it was a logarithmic value, but
Okay.
uh,
Okay, let's fun next question, sir. Okay. Um, or to compare. So can you explain uh this one? Skip on if affect what order comparison? Oh, this one already just explained. Okay. This one, inserting total.
yeah,
What's this? Why it has this plus together?
V plus V. So both of these uh, both of these values like V plus and V star, uh,
Mm,
they I think adding them represent the whole set of V.
no. So do you see the V plus V star equal to
Yeah,
V? No,
yeah,
no. Uh, V plus V star should be a
yeah.
subset
Belongs
of
to
V
V.
plus. It's wrong.
Oh
Okay.
yeah.
So,
But we have both.
so, so why this? Can you explain this? Why the simply this? Simplified. My version has E plus times log E.
It's because the we are using the only the edges which are like subsequent edges uh of the insertion.
Mm. So why here is has a log E plus.
Uh,
Okay. So
because
the
like
go on. You remember something?
yeah, so the mean priority queue is also implemented as a tree.
What? Particle implement
Yeah, it was where it like implemented as a tree.
heap cube
Sorry, heap.
heap.
Yeah,
Okay. Okay. Particle is a heap. Okay. But why is the particle? Why is log E plus, not log E?
Because we don't need to examine all the edges. Like E means all the edges of the graph.
Why is the times E plus like this?
Uh, Times E plus. That I'm not sure of.
I hope you can explain it one by one clearly, not ask you like this way. Okay, go on. No, come back. So ask you the index space. So is traversal is n. Oh, so can you explain why here don't use a big O symbol?
So,
Because this is the coefficient. If we ignore its coefficient, it's still this one is still same, right?
yeah, but it's for the labeling world, right?
Yes, I asked you why.
Uh,
Why here we don't use you don't use big O?
because the labeling word is a finite set. That's why.
Anybody knows why here I don't use big O notation? So I use I listed this coefficient 23 words. This one use 15 words. Why? Anybody know? Do you know this? Oh, so everybody is quiet. Okay. Uh, the big O notation has a limitation. See, big O notation always ignore this coefficient. Only ignore coefficient because it's trying to describe how fast it increasing. It doesn't care about coefficient here. But in the space, when in space, we suppose n is really large. We want to know how much memory it takes. That's why the coefficient is important here. So we normally, and it's easy to calculate. We normally will use the coefficient to so that how much memory it takes. Even this and this index space is still linear time, right? But not linear. It's on, but we more care about the coefficient here. And tell us how much memory it takes. This is the limitation for the big O notation. It's omit the coefficient. But sometimes we need this coefficient. Mm.
Uh,
Any question? No? Okay. Mm. I think you explain all this. Okay, next one.
okay. So
Mm.
what the table is telling us? So
Mm.
one is the ordering term vanishes completely. Uh, Two, exactly one logarithm survives,
Yes.
and we will see it in the later. And three, the uh, three is the what was that? Um, no, no, we can ignore this.
Yeah, yeah. Just go to part B.
Okay, so this is the main part of the presentation.
Mm.
So we will see why the maintenance is O of one amortized. It's a it's a bit simplified for the sake of the presentation.
Mm.
So what is the order maintenance problem? So we keep a list of L items, and basically, as we can see, we have like three operations, and the order maintenance problem is basically we have to do the operation in O of 1 time.
Mm.
We need to get the order which will tell if B comes before D, it will return true. Then we have insert, where we insert C before X and we delete B, like we delete a value from the list. So these are the three operations, and we
Okay.
need to do them
Mm.
in or on constant time.
So you said the order is called far often than the other two insert and delete. Why? Why the order is called always called and much frequently called
So
than others?
so this is basically the main purpose of this data structure, where uh, we need to know if a value comes before the other one.
Yeah.
So that's where
Why?
the
Yes. Why is often called? It's a frequently more times called than others. This is the question.
because we need to constantly keep update the structure.
I are you sure you answer this question? My question is why order is called for more often than other two?
uh, in base for the I mean, for the context of core maintenance.
Yes, you see the order not limits to the core maintenance, but oh yeah, it's for core maintenance. Why?
Yeah, here we described why it's there. So the order runs on every neighbor test in
Yeah,
the inner loop.
yeah.
That's why. And insert delete where only fires when a vertex moves from one core to another.
You explain when is order happens, when insert happens, when delete happens, but you didn't explain why the order is more often than the other two, right? My logic is right.
Uh, yeah.
Okay, you explain half. Still good. Go on.
Okay. So why this data structure, and why not just use linked list, array, or balance tree?
Oh,
So
that's good comparison. So, okay, explain why. Why the linked list is Owen? Order is Owen?
so if we want to insert something, so basically if we want to uh, like get the order, we need to traverse the whole linked list to get it.
Mm. Okay, good. Your Owen is a best case, worst case, or average case?
So it's basically in average cases.
Yeah. So when every time you describe your time complexity, explain is in which case. So what is the average case you mean?
What is the average case?
Yes.
We the average case can be considered if maybe the item is like middle of the list.
Yeah. It's still Owen. Yeah. The coefficient is the half of that, but the coefficient is ignored. That's Owen. Good.
Yeah.
Okay.
The
Explain
best case will be if it is like at the far top of the list, then it will be best
mm.
case, but that really happens.
Although why is the order operation in array is Owen? Explain this.
We can get the value just by the index.
Okay. The index is in the position, so insert one item, shift everyone out. The insertion is correct. But how why is order is Owen?
Like if we want to get any value from the middle of the linked list, we can just call it by the index.
No. This way it says compare the orders. So give it a array, right? Give it a array. It has so many values. 1, 8, 2, 7. right? Can you compare these two values? The orders.
Yeah, but if we know the index of these two values, we can compare it in constant time, right?
Oh, yes, yes. Yeah, you're right. Okay, good, good. Mm,
And for a balanced tree, it's always log n. In average case, it's the height, sorry, it's the height of the tree. So
mm.
nothing is constant here.
Okay, so what is the balanced tree? Now can you answer? Now, what is the balanced tree?
So basically, a balanced tree will be where uh, the left and right side of the tree is almost properly balanced.
Mm.
Like it's not a chain.
Okay, good, good. Uh, let's say in the balanced tree you have this three is log n. Yes. In which case? Best case, worst
In,
case, average
in
case.
average cases.
What is the average case?
Uh, in average case, it means like it's not in the root of the tree. So maybe somewhere down in the like left or right
Mm.
subtrees.
How about the worst case? Is it still same?
Yeah, it will be the height of the tree.
Height of tree is still same, right?
Yeah,
So you can say this is bounded for worst case. This is bounded for worst case.
yeah.
But okay, good. I think then you all three cases are your understanding is good. Okay, go on. Okay, we don't have time. We must be faster. Okay, go on. Mm.
We have a lot of slides. Okay,
Mm,
so the best we found here is log n, but we need O of one. So let's see if we can find anything better.
mm,
So basically, to fix this issue, uh, we give every item an integer level in increasing order, the increasing order along the list. So the order becomes one comparison, and the worst case should be O of one then.
yeah, go on.
Okay, so since we have the label, uh, we can do all of the operation with the help of the labels.
Mm,
Then we have this algorithm from 3.3. It's just there, and uh, this algorithm actually defines all the three operations: order, delete, and insert. Uh, so this algorithm needs to be correct because of the proposition one. So first we have the invariant one, which states for every pair x and y in L means in the list, x precedes y if and only if label of x is less than label of y. So basically that means if the label of x comes before the label of y, x comes before the y.
mm. Also,
And
where you get this code?
uh, I think it's just the like representation of the insert, basically in general.
Okay, this code is good. It explains the basic ideas. It
Yeah.
ignore all of the details. Okay, I go to washroom. Back 1 minute. Okay, go on. That's it'll be faster. Okay. I said your algorithm here is good. So it ignores lots of details. It directly shows ideas.
Yeah.
Yeah.
So then we have the amortized cost.
So what
So
is amortized?
the amortized means if we have if we have like mm, we have C amount we if an operation cost C
Mm,
and we have to do it n times and the total number of the total operation actually results in Cn, then
mm,
it's an amortized cost. So here some in between, some cost can be a greater or
mm,
lower, but
mm.
ultimately if it's Cn. So basically
Mm.
that's his amortized costs.
Good, good, good.
Hmm. So also like we have to remember that amortized cost O of one doesn't mean every operation is fast.
Mm,
So maybe some one insertion can be a bit expensive.
mm.
So but in general, every uh, every operation should result in O of one.
Yes. Good.
Then we have the leveling. The leveling was so it's a like simple demonstration
Mm,
of how the labeling is done. So the labeling actually means is like we will put a label in every item of the list of the ordered list, and when we need to insert one item, we insert it in the middle in the free space. So we can see for the linear worlds, there is no free space at all. So every time we need to insert, we need to move everything in the subsequent. Uh,
what do you mean over here? I'm confusing. What do you mean over here? Here. What's the U? What's the N?
uh, it's just here to represent the worlds,
The total
the
number of
universe. Sorry.
total number of words?
Not worlds, like in the labeling domain, the labeling universe here.
I okay. Yeah, I cannot understand. Okay. Uh, it's a insertion time complexity here. Relabeling.
Relabeling time complexities.
Relabeling is almost at relabeling time complexity. If
Sorry,
it is the if it is four, if it is four, why it is log n squared?
because there's no room and you need to relabel every time you put any new number.
If there no rooms, no room, it must be move. It must move all of the. If I insert here, it need to move all of the items to the right. So it should be n.
Yeah, but if we like if we move in if we insert in a random position, like suppose we need to insert here, then we
So
need to
where,
move.
yeah, you are talking about the average case where but here is you use the upper and lower bound, including the worst case. The worst case in the front. So it's n. It's n like this.
Uh,
Even if average case in the middle, it's a uh you need to shift all of the item to right side because there's no room for them.
yeah, I think it should be off.
Okay, here's a so here is the most difficult part of the time complexity explanations.
Which one?
This part is if there's no labeling, it must be on, and if there's a gate, there's a gate. here, escape, you can insert it beside them.
Yeah,
And that is login. Yeah. So
yeah.
problem is, what's the gate and why it is login?
Sorry.
Why it is login and what is the gate? How large the gate is?
So the login is the like lower bound for ins relabeling. Like
Yeah. Why it is login? Yeah.
mm, uh, because be, because we don't need to like mm, okay, how do I explain it?
Mm.
Uh,
Do you want to skip this question? Honestly, I don't know this. I read that paper. I cannot understand. Yeah. Can you explain clearly why it is login?
I don't think I can explain clearly.
Yeah, I say it's and the first one this you want to explain this. I think you only explain this take you half hour. The purely theoretical computations of why it is login, and the game here should be n. Yeah,
Yeah,
the game is n. So you have n items. You have n items. The game is n. So totally you need the label space should be n square. N square.
I think that that has something to do with the free spaces in between.
Free space. Yes, yes, free space. So free space. If the label space n here, every time you insert to the every time you insert it, so you assign the label is in the middle. We talk about the worst case. Every time you insert in the middle, right? So you can insert log n. You can insert log n that
Yeah,
without relabeling. But
that
when the relabel triggers, the relabel itself still costs log n.
yeah, I have that in the next slide.
Okay, go on, go on. Go to the next slide. Okay, explain why.
So, so a lower bound must defeat every algorithm. Since we are talking about lower bound, it should be true for every algorithm, like
Mm,
including the ones which nobody has came up with yet.
mm,
So we need to prove that. Uh,
mm,
so basically, the here we are using the adversary strategy. So basically, the algorithm chooses the label, and an adversary chooses where each new item goes. Uh, so the adversary moves after seeing the label, and it always aims at the weakest spot. That is where the worst case statement. So basically, what the adversary does is it tries to put the value where is the densest part of the structure. As you can see, uh, here it's crowded.
mm.
Here we are putting in the crowded region. And then a relabeling triggers.
Yes, this is a good example. And the
Yeah,
relabeling takes a log n on almost at a time, right?
yeah.
This I really want to know why.
Yeah, I didn't dig deep into the login part. So basically, this proves like the type bound is basically login, and the login is the worst you can get.
Mm, okay, so it's because my paper is based on this solution. It's a log n.
Yeah.
Mm.
I didn't realize it to be so complex like when I dig into
No,
this.
I say it's complex to me. Maybe you read it, you find another way to prove it. That's our new contribution. I said the contribution is always unexpected. I thought it's a difficult, but maybe not for you, right?
Yeah.
Mm,
So basically, we see how the login works,
mm,
and you can ask, okay, then why not just use some enormous labels where we have tons of free spaces in
mm,
between? Then what happens? So if we, as we saw in the slide, if we use the exponential universe where we have room everywhere, but there we comes into another obstacle.
mm.
A universe of size 2 to the power theta of n cannot be written in like in a machine. So the number becomes way too big to like program it into a machine. So that's why we can't use some enormous level.
Good. Good explain. This is
Okay,
that's
so
that means our label must be fit into the machine words,
yeah,
32
yeah,
bits or 64 bits. And
yeah.
we assume that 32 bits comparison only takes constant time. That's the big assumption of this algorithm. Without this assumption, there's not a constant time comparison. Go on.
Okay,
Mm.
so then we have the two level of levelings. Two level of levels.
But why we need two levels?
Uh, so basically, the two level is the trick which allows the O of one time complexity here. So
Yes. Mm.
this part is also the
Why two levels and we have a O1 time complexity?
we will come into this.
Okay, can we come to that one? We don't have time. This is the key points to explain. Okay.
So this is how we uh, come to the O
Mm.
of one insert. So basically, every time when we are relabeling, we are splitting mm, the global G lib, what the paper calls it, global
Mm.
labels, G libs.
Mm. Mm.
So uh, what happens is basically we split it in S times, maybe. Uh, okay, so basically the splitting the group costs log n,
Yeah.
and
Sorry,
we
splitting the group cost longer. Splitting the group cost the constant time. One group split as two groups, right? And then insert into the list.
sorry,
The split group cost a constant time, I remember.
it
And
was
splitting the group costs constant time. But but the relabeling but the relabeling costs a log n.
yeah, basically that, like splitting and relabeling.
Yes.
So
Mm,
it took log n time,
mm,
and a group of size only overflows once
mm,
every, like, so a group of a group of size S only overflows in S insertion. So basically it becomes uh, log n by S.
what is S? Yeah, here.
S is the size of is a group size.
So your so the time should be like this, right? The group size. What is group size?
Oh yeah, that's what we choose the group size to be equal of log n. So that becomes 1
Are you talking about the best case, worst case, or average case?
in average case.
Are you sure? Why
Uh,
is the average case? What do you mean of average case?
Here for the group size
Yes.
is the
Okay.
What?
All we extend here is for worst case. Because if you say average case, that means that we can construct some more worst case examples. Worst case examples that is not in this average case. So we the time context analysis always talks about the worst case.
Oh, okay.
But sometimes we might more care about average case, like the graphs. So we don't have a worst case graph like chain graphs. We don't have this in real world. But this is data structure. This data structure. So what is the worst case? What is the average case? Then when you talk about this, you must clearly define this. The data structure is always discuss the worst case.
Okay.
Mm. Like good. Most clients prep. But here so is the worst case. Go. Anything to do, we take a 1 hour, more than 1 hours. Oh,
No, like
everybody gets tired. Okay.
this is the most of it, and
Mm.
then just
Okay.
answer it.
Uh, I guess you did a great presentation there, and you didn't answer some of my questions. I understand. I understand. And the problem is you try to cover too many things. Only this part, only this part. The order data structure itself, it can give us a 40 minutes talk. Yeah, not just this one. So it's going to depth is much better than uh cover too much.
Yeah, like
Mm,
this was more like larger than I expected to
yeah,
fit into
good.
this.
Good work. Good work. And anyone has questions?
I think others had to go.
No.
They,
Okay. Your organization is not very good, and because I have background, I can understand your talk. But for some other ones, if they don't have some background, it's impossible
yeah,
to follow
yeah,
your talk.
that I understand because if I had to put all the context, then maybe just the context will take a like 1 hour presentation.
Yeah. So it's if you send me early, so I can help you to cut it. But you didn't. That's okay. You still did for the course. For this course, you did a great job, right? You did a great job. Good. But this presentation is not a good style in some conference talk or some talk to some students or some people without any background. It's not friendly.
Yeah, I
Mm,
understand. Like,
mm.
but I didn't like find way to like include the more context without like increasing the slides.
Okay. Uh, any questions?
No.
Mm. Okay, that's for today's talk. Mm,
Okay.
mm,
I will send you the report
mm.
later today.
Yeah, yeah, send me.
Okay.
Yeah. Uh, take a break. See you later. Mm,
Yeah, bye.
mm.